So I might give a short introduction for myself. I'm Jian from TU Delft. I am a PhD student and working on the database acceleration using FPGAs. And today I'm going to show you an application of the OpenCAPI, which is the database acceleration. So let me start from our current project. Uh, we are going to make a heterogeneous database that can make use of the FPGA. So let's assume we have many applications running on top of the CPU, which would be the Power 9. And when you have some queries, you need to map the SQL down, and then we go to the storage to fetch the data. And we would like to store the data in an NVMe storage device and go to an FPGA that perform the decompress filtering. And also we have this Fletcher framework, uh, which is from Johann Pelpenberg. And this one can help you to write the table in Apache arrow format. And from the data processing side, we add another FPGA to do the data processing, or you can also merge these two FPGA into one. And we also use the Fletcher framework, but for this part we use the read to read the tables from the shared memory, and we performs the actions in the FPGA. We can do some sort, join, skylight, etc. And with this arrow table, you can also offload your offload the task into the GPU. And this one will also take advantage of the arrow table to help you to avoid the serialization and the deserialization. And we are going to make a scalable heterogeneous accelerated database. And we haven't given a name about this project. Maybe we just call it Shade. So today our presentation will focus on the decompress filter part, which is pointed here. And the motivation is nowadays in the big data processing or data analytics applications, there are many data intensive tasks such as sort, join, partitioning, filtering, aggregation, histogram, or maybe data reformat. And a very common feature from these among these tasks is they have a lot of data movement. You need to move the data from the storage to the CPU, from the CPU to the network, or from the network back to the memory. So if the data amount is really large, this will become a bottleneck, especially when your data comes from the storage. And you have to face the fact that even though you can put your database in memory, you cannot avoid the first step, which is fetching the data from the storage. So to solve this problem, we have explored some solutions. One of them is to use the decompress filtering. So the same architecture, in between the storage and the host, we put an FPGA and perform the decompress filtering. And instead of storing the original data in the storage, we are now storing the compressed data. So the data amount will be much less than the original one. So now when your CPU need to fetch a bunch of data, you only need to move a small amount compressed data and do the decompression inside the FPGA and then do the filtering. And then forward this filtered data to the host. And this idea has been proved by Netizard a couple of years ago. And there are more compression and decompression algorithm have been implemented in the FPGA already. So these days I has been asked some questions. What why are you still doing something others has been finished a couple of years ago? So simply question, and simple answer is we are doing something else or missing here. We do the Snappy decompression, and Snappy is a new decompression algorithm widely used in the big data systems, and it supports packet or ORC. That's why we still need decompression. But another critical question is, so now we have the OpenCAPI. It has much larger boundaries. Why you still need to compress your data? Why not just forward the original data? So I would say you can still save the storage space if you have 2 times compression ratio. Then you can save half of the space, and you can store twice as much data as you can, right? And a further answer will be actually 25 gig speed is not enough. So people are always graded. When you have CAPI 1, you said 8 gig that's not enough. We want more. Then we have CAPI 2, so we have 16 gig now, and then we say we are not in. That's not enough. So we have OpenCAPI now. That's 25 gig. I actually want to steal a slice from Mayon, but I haven't found it anywhere. It shows the OpenPOWER roadmap, and in 2020 plus, they will have Power 10 plus CAPI 5 or something, and provide you 50 gig. So actually, we always asking more boundaries. So in our architecture, we can give you, let's say, we can amplify these boundaries. So if your compression ratio can reach 2, and you can decompress the data as fast as you can, then you can get twice as much as boundaries. So in OpenCAPI, you can have 50 gig. And then you don't need to wait, let's say 3 years later until IBM publish the 50 gig. And when IBM have this 50 gig available, you can have 100 gig. That means you are always, let's say, 1 generation ahead of the work. So what is Snappy? Snappy is a compression algorithm open sourced by Google more than 10 years ago. And it's LZ77 based, bi-level, and it's lossless. It is widely used in many big data systems platforms, and support packet and ORC, and it has lower compression ratio, but the speed is fast. And this number from the Snappy official website, they give 500 megabyte per second decompression throughput from one code. And that's not enough because we have 25 gig. So our goal is to have OpenCAPI speed decompression ratio inside an FPGA. So the following slides will be some details about the Snappy compression and Snappy decompression. Compression and decompression algorithm is actually a very simple algorithm. It just found the repeated sequential from the previous one. So for example, we have this sequence A, B, C, D, E, F, G, H, and then we found a repeat A, B, C, D. So now we use this tuple A4 to replace this. Then we can stream the data amount. So for those, it's not in the, we cannot find a repeated sequence. We just keep its original data. So we call this the literal token. So the compaction process is like this. So the ... means some previous, let me use this. The previous sequential is here, and when you read A, B, C, D, E, F, A, G, H, and you cannot find any match before, so you create a literal token, and then you keep on finding the match. So you found another ABCD, then you find a match here, and that's a copy token. So we are now using this literal token plus copy token to replace the original data. And the decompression is a reverse process. So now the data you read is token by token, and for those literal token, when you read it, you only need to grab the original data. And sorry, for those copy tokens, you go back with this index 5 a step before, and found length of 4, then copy this into add it into the end. So by this process, you can decompress all the whole streams. So there are some details about the Snappy compression and decompression algorithm, and as we see it, there's something missed here, which is the history. So you always need to find back to the history to find the repeat sequence. So the setting of the Snappy is 64K byte, and if I don't know whether you are familiar with the LZ77, that's a slide window. The history is a slide window, but in Snappy here, it's a fixed window. So when you finish with the construction of the history, that means you finish with this block of data decompression, then you start a new 64K blocks. So the token, there are two tokens, copies and literals. The data both not exceed the 16.4 byte, and we also did some calculation on the size of the token. The token size will be varies. Some tokens 2 bytes, some is 3 bytes, some is 4 bytes. So, and for the literal, if we count the size of the original data, then the size of the token will be much larger. So the average here is a little bit less than 4 from a couple of benchmarks. And the data is very highly dependent. That means the token, one token need to read the data that from the last token. So in FPGA design, we want to store the history in the BRAM, but BRAM is block by block. So you cannot use small granularity. The smallest one is 4K bytes, so we need 16 of those to construct a history buffer. So during this design, we face many challenges, and these 4 are the let's say the most important one. So first of all, you need to deal with different type of token. For literal token, you only need to write your data in the history. But for those copy token, you need to read from the history first and then write it back. And for the other one is you need to deal with the various size of the token. So for literal tokens, they have three types of constructions. These represent different size of the literal. For small one, you only need 2 bytes. For large one, you need a medium one, you need 3 bytes, and larger one, you need 4 bytes. And for copy, is similar. And when you need to copy the data from the near part, then you have small offset, the index. And if you need to copy data from very far, then you need a long byte to indicate the index. So this is the size of the token. And when you have very size of the token, that means it's hard for you to recognize which one is the token. You cannot set I cut it 2 by 2 by 2 by and do a translation in the same cycle. It's impossible because it varies. You don't know where the next token start before you recognize the first token. And but in FPGA we can do this in parallel. So we just explore all the possibility. So for example, if we grab an 8 byte line, it's possible that every token start from every byte. So we just assume that all the bytes are a start of the token. So at the end, when we have the first boundary decided, we can know which is our correct choice. So by this method, we can, let's say, recognize the token boundary in every cycle. We can recognize a whole line. And the most important one is how to parallelize this token translation, and how. So if you want to translate the token into the data itself, you need a read from the history and write back to the history, or you don't need a read, just write. So if you want to execute a multiple token in the same time, then you need to solve this dependency. So let's say token 1 and 2 are issued in the same cycle, and token 3 and 4 issue the next cycle. So what we need to deal with is this read and write dependency. So for read, there is no dependency because you don't need to change data. And for write, we found that it never has dependency because you always add the token translation, I mean the data, at the end of the history. So you never write a same byte by two tokens. And for those write and read, you can just doing forwarding. It seems that there is no dependency here. But in FPGA, these things are different because the history is stored in the BRAM, and the BRAM only offer you one read port and one write port. So when you need to write, when two tokens write same blocks, then you have the address conflict. For this write and write, the first write may hit the second write in the same block. For this, we can use write combination or combination write. And but for this one, when you need to write different line in the same VRAM block, you cannot finish it in one cycle, right? So for this one, you have to stop these two tokens. Maybe let the first one do the write and then let the second one do the write. And the read and read now becomes a problem because the read is randomly. When you read the data from the history, you don't know where it is. So we did some statistic that most of the adjacent tokens will get a conflict on the address from the read. So for this one, I would say you have to stop one token translation until the first one is done. So we have talked about putting two history, but that's not very scalable because if you want to have more token translate in the same cycle, then you need more history duplicate. So it seems that there is no solution. And if you want to key up with the OpenCAPI boundaries, then we do some calculation already. So you need 13 instances and the frequency should reach 250 megahertz to consume the whole OpenCAPI boundaries. And this is impossible. We try in the latest FPGA, the KU37P. It's impossible, so we try to find another solution. And our idea is very simple. So we have the first one is the read conflict. So we can see that the conflict only occurs in the middle two blocks, not the first one and the second one. And also this write, it only occurs in one VRAM block, not the rest. So why not just let the rest do it themselves and just block this one? So now we have a final granularity one to do this translation. So we propose this architecture. So the three key technique from our architecture is first we need to do a two-level process. So first of all, we need to recognize the token boundary and the token information from from a couple of bytes, let's say 16 bytes. Then we need to translate this token into BRAM, command. So for example, if you have a token writing these 3 BRAM blocks, you are getting 3 BRAM commands. So the second one is to parallelize the BRAM operations. So we specified 16 of these BRAM sets, and also we put the 16 independent control logics around this BRAM, and we have a readless execution model. So I will explain these two in the same slide. So for the literal token, you actually get a write command, and for those copy token, you have a read and a write. So the write always successful, but for those read, it's possible that the data is not there yet. So for those not ready one, we just let it roll back. We don't stop them, we don't block, just use a recycle FIFO and put it in a queue and wait for the next round execution. We have some implementation results based on the KU15P. So the most resource consumed is the LUT. It takes almost 9% of in one FPGA, and we do some benchmark. We compare the official benchmark from the Snappy. We get a 5 GB per second in a single instance, compared with a single core i7, which is 500 megabytes. So it seems that we get 10x speed up. Yeah, our project will be open source, and the link here is the project for this decompress filtering, and for the whole project and the other components, we will put the link inside this link. And for those who is interested in our projects, you can read our paper, and if you still have questions, long discussion, you can send me email. Thank you.